Our neighbor Mars. That shiny little dot in the sky is called the curiosity of mankind for a long time, due to its numerous similarities with our planet. Rovers have already landed on it to study its surface, and people will walk on it one day. But these giant leaps all start here, in our home, on planet Earth.
McGill Robotics is an umbrella organization of teams designing robots for international competition from McGill University in Montreal, Canada. It has existed for 2 years and has grown to 150 members to now have a Mars Rover team competing in the University Rover Challenge near Hanksville in Utah, an autonomous underwater vehicle team participating in the RoboSub competition, and a business team taking care of McGill Robotics' finances, sponsorship, marketing strategies, and performing outreach with younger students of the Montreal area. This year's was the Mars Rover team's first. Last October, more than 50 undergraduate students were recruited and divided into 3 divisions: mechanical, electrical, and software, which were then further divided into sections. Maintaining such a structure was very important in a large group like the Mars Rover, as it allowed efficient work distribution and planning throughout the year. In addition, using the professional Podio project management platform has eased the communications across the whole team. Together, in just a few months, the team designed from scratch its very first Mars Rover, Artemis.
The mechanical division is made up of 3 sections: drive systems, the arm manipulator, and frame and science. But before we jump into these 3 sections, let's first take a look at the new technologies we used this year and the different strategies we took to organize ourselves.
The mechanical division is responsible for the designing, manufacturing, and testing of all mechanical components of Artemis. The design phase includes conceptual design period followed by CAD design. The CAD software of choice was Autodesk Inventor, for its user-friendliness, allowing new members to learn how to CAD intuitively, while also providing us with useful design tools such as stress simulation and parametric optimization. We also kept in mind modularity, ease of servicing between tasks, and the needs of other divisions in a design process. As soon as the first iteration design was completed, we moved on to planning for manufacturing. The complicated parts were CNC machined, while simple parts were made with conventional machining. We also heavily utilized new technologies such as 3D printing and plastic laser cutting for lightweight components that do not undergo heavy stresses and for prototyping. During the testing phase, our main job was to assemble and disassemble the rover to cut down on assembly time at the competition.
Our arm has been designed such that it can be reconfigured on the fly, either to optimize dexterity or lifting capabilities. The arm can be broadly broken down into 2 main sections: the base arm and the swappable end effectors. For the base arm, we decided to use linear actuators in order to allow the arm to mechanically self-lock. The links of the base arm are entirely made out of CNC machined aluminum plates. This allowed us to incorporate an intricate set of lightning holes into our design in order to minimize the weight of the arm as much as possible. Our arm has 2 primary end effectors, a shovel and a gripper unit. To optimize the arm for lifting heavy objects, such as during the astronaut assistance task, we can directly mount the gripper unit onto the base arm. If instead we want to optimize dexterity, we can add a wrist unit between the base arm and the gripper unit. Doing so gives the arm a total of 6 degrees of freedom. This will allow the operator to easily complete the panel servicing task with minimal repositioning of the robot.
The frame and extremity section is responsible for various components on the rover, mainly the base plate, the electrical enclosure, and various custom-made pieces. The base plate is CNC machined out of aluminum. It is both light and strong, and supports the differential, the arm manipulator, the batteries, and the electrical backplate. An aluminum enclosure houses all of the electrical components, and when combined with rubber seals, protects its contents against heat and dust. Furthermore, 3 fans provide continuous convective heat dissipation across the whole system. A mast positioned at the center of the rover provides support for the HD camera's pan and tilt mount, for the IMU and GPS housing, and for the antenna's base.
For our drive system, we designed a unique suspension frame, differential system, and drive assembly. The suspension system is designed after a linear bogie suspension system to allow for better climbing capabilities in comparison to its predecessor, the rocker bogie suspension system. It uses a 4-bar linkage to translate horizontal motion into a vertical motion over obstacles. The suspension system can also be transformed into a 4-wheel drive by locking the suspension bars. A detachable differential at the center of the rover is used to stabilize the rover's frame, even with changes in its weight distribution. Our drive system uses 6 brushless motors held inside of custom wheel hubs, providing extra clearance under Artemis to easily traverse obstacles. 4 servo motors are connected to the front and back of the drive system to allow for independent steering.
The science enclosure was designed as an assembly line with soil samples collected and analyzed for traces of basic biological molecules, then sealed and replaced by the next sample. This simple design was chosen to maximize the amount of data collected while minimizing the number of motors. A rotating base plate facilitates testing and protects wet samples from rough terrain. A probe mount consists of a pH probe and sets of capillary tubes prepared using solutions used in testing for proteins, lipids, and carbohydrates, as these were the simplest useful tests. The probe mount allows for multiple sets of capillary tubes to be submerged independently at discrete depths, driven only by a stepper motor. The natural motion of the rover mixes the soil sample with distilled water in the test base, so the humidity test will be done on the arm using a humidity probe attached to the soil retrieving mechanism. Further benchtop analysis will be conducted at the bench after the sample return to verify data.
The electrical system is divided into 3 main sections: power, interface, and motor control. The electrical system on board Artemis has been designed to be extremely rugged and modular while maintaining an extensive range of function. Our custom power, interface, and motor control boards are designed to connect together via PCB backplane and card edge connectors. This backplane has been designed to route power as efficiently as possible while keeping sensitive signal lines shielded from all sources of EM interference. This backplane design has allowed us to reduce wiring inside the enclosure by as much as 100 feet, giving us more room for ventilation and other devices. Artemis's PCB cards are designed to be extremely self-reliant and can perform many tasks independently without loading the rest of the system. This includes PID control, state estimation, power and thermal monitoring, and fault detection. Each board features multiple safety mechanisms to protect the system from faults, shorts, and interference.
Motor controllers designed in-house control all the 20 motors on board Artemis. First, we have 6 brushless motors used for rover propulsion that are controlled by 3 driver boards. These boards uses feedback from Hall effect sensor and encoders for the PID control and the odometer tracking. For the base of the arm, we're using 4 brushed motors that are controlled by 2 brushed motor controllers. In addition, we're using 3 stepper controller for the end effector and 1 stepper controller for the science enclosure box, all controlled by 2 stepper driver. All the joints on the arm are fitted with 13 bits absolute magnetic encoder for position measurement. Each board features 1 microprocessor that generates all the motor commands and implement the PID control. Finally, 1 single board controls the 4 steering servo, 2 pan cam mount servo, and 1 science enclosure servo.
The Sensors and Interface section is in charge of the sensors, instruments, and communication equipment that will be used on the rover. Artemis has 2 radios. One of them is a 2.4 GHz radio, which will be used for high-quality video streaming. The other is a 900 MHz radio that will be used for telemetry and control. Artemis will have a total of 6 cameras, 4 hazard avoidance cameras that will be used for close quarters navigation and obstacle avoidance. A panoramic camera will be placed high on a mount in order to have an overall view of the field. Finally, an arm camera will be used for feedback for arm and end effector control. All cameras are connected to the onboard computer via our custom-designed USB 3.0 hub. Onboard Artemis, there are multiple microcontrollers which control its various systems. Communication between these is done using a noise-resilient RS-485 bus using our very own custom-designed protocol.
In the power system section, the power distribution is comprised of a battery board and a DC board. The battery contains a hot swap system for easy battery exchange while Artemis is on. It also contains a load sharing for even load distribution across all batteries for safety and for longevity of the batteries. It also contains a power monitoring system to monitor the batteries, voltage, and current offshore. The DC board utilizes a universal layout. Each board is made to be flexible and interchangeable by only replacing a specific components. This can greatly help during emissions as only the components are needed and not the complete sets of boards.
The software division is divided into three sections: control system, state estimation, and human-computer interaction.
The software system we developed for this project is composed of several independent running programs that are brought together using the robotic operating system. This framework is a collection of tools and software packages that help us design large-scale software applications for robotics systems. It allowed us to create our control system, our state estimation system, and our human-computer interaction system concurrently, and to interface them with very little effort. ROS is the leading framework in development of robotics software system, and this is why we decided to use it. It provides some great tools for data visualization and analysis, which allowed us to streamline our development process. ROS uses the TCP/IP protocol for inter-process communication. This means that processes can communicate together as long as they are on the same IP network. When combined with the 2.4 GHz and 900 MHz radio, the command station can communicate with the robot as if they were the same computer.
The control systems is the most critical part of the software in Artemis. It is the collection of programs that forms the link between the user telling the rover what to do and the actual physical parts of the rover enacting that command in unison. The control systems handles the wheels of the rover, enabling our 6-wheel Ackermann steering geometry, as well as simple point rotation. It also governs the robotic arm, computing inverse kinematics equations to administer changes to each of the joints. As the arm motors are speed controlled rather than position controlled, we also include PI loops in the software to make sure the motion of the arm is smooth.
Although the rover does not require autonomous control, providing accurate location data can make the driver's job a lot easier. By combining data from our GPS, IMU, and odometry in an extended Kalman filter, we can achieve much greater positional accuracy than any of the sensors individually. We can then present this information visually to the team. We chose to use the extended Kalman filter because it is ideally suited to linear motion, but is also flexible enough to adapt when the rover undergoes rotation or acceleration. To achieve accuracy during nonlinear motion, we had to develop transition models for the position as well as the sensor noise. Although writing and tuning the filter required a lot of time, research, and trial and error testing, we believe that the result was worth the effort.
When designing our control software, we focused on two major aspects, namely having an intuitive and easy-to-use software and having all the critical system information displayed efficiently. To control the movements of the robot, the operator uses a joystick and a touchscreen laptop. We chose the joystick controller over other types of controllers, namely the PS3 controller, because of the long travel distance on the analog sticks. This gives us a much better resolution for precise manipulations. Additionally, the high number of buttons on the controller allowed us to map all the functions directly on the joystick. Our control software is programmed with Python, which is easy to read and understand. We used the Pygame library to interface with the joystick and the PyQt library to lay out all the graphical elements. It is a wrapper over this C++ Qt library, so many tools exist to design and lay out components on a window.
One core specificity to McGill Robotics is its dedicated business team. As members of the team change over the years, with different skills and vision, the brand outlives. We decided to brand McGill Robotics to convey in the long term experience and legitimacy. In particular, we developed a solid marketing strategy to ensure our exposure and the exposure of our sponsors across all social media platforms. Sponsors play an important role in our team's performance. McGill Robotics is a 100% student-run design team, and it is up to us to raise funding. It is quite a challenge, but with a solid team effort, we managed to cover all our expenses as well as bring 15 people to competition. One final aspect of McGill Robotics is its dedicated outreach effort. We often visit schools in the Montreal area, showcasing our robots and providing mentorship. By doing so, we hope to inspire the next generations of engineers and scientists as they set out to build robots of their own.